Okay, so here I go in my second mini video, starting to discuss the chemistry of alkynes. So let's recall that alkynes are compounds that they have two carbon atoms with sp hybridization side by side, and those carbon atoms are forming one sigma bond and two pi bonds. Let's recall that you have alkenes with one double bond, and that counts as one unsaturation. You can also have rings. One ring also counts as one unsaturation, and the alkyne triple bond that counts as two unsaturations. There is a simple classification of alkynes as being terminal alkynes or internal alkynes. So terminal alkyne means that the triple bond is at the end of the chain, while internal alkyne means that you can have a triple bond somewhere in the middle, and so that will make it internal. This time I put some white pages in between, so that allows me that if I want to discuss some structures, I can do it in that way, right? For instance, I can write down. I'm having some problems with the choice of the pen. Okay, so there we go. There we go. So and then here we have a case of a terminal alkyne. And here we have an internal. The terminal alkynes will be particularly useful for synthesis. And that is because you have one hydrogen atom here that is relatively acidic. So if you go to look in your table of pKa values, you will see that the pKa value associated with this terminal alkyne is around, pKa value is around 25. So that means that with some bases like Na plus, NH2 minus, you should be able to deprotonate an alkyne, a terminal alkyne, and that would allow you to use that acetylide anion as a nucleophile to react with alkyl halides, and we can form compounds that they are longer. So that will be a standard way to synthesize more complex looking molecules. Obviously, you cannot deprotonate an internal alkyne, right? Why not? Because all the hydrogen atoms that we have in this internal alkyne are not acidic enough. The pKa value of those will be more in the range of, I would say, like 50. So there are no bases that will allow you to deprotonate those. Well, so the other thing that we need to discuss is the nomenclature of alkynes. And for that, I will let you read by yourself the initial sections of chapter 9. Chapter 9.1 deals with the nomenclature, and also in OWL you will get some basic clues on how to handle this. So we follow pretty much the same rules that every time I need to choose. Okay, so let's say if you have a structure like this, and I have a couple of methyl groups here. So what will be the name of this? My longest chain will be 1, 2, 3, 4, 5, 6. So because I have a triple bond between carbon 1 and 2, so that will be hexane, but I change the ending from ane to ine, so it will be hexine. I need to indicate where the triple bond is. It's between carbon 1 and 2, so it will be 1 hexine. And because I have a couple of methyl groups in the carbon 3, so that will make it 3,3-dimethyl 1 hexine. Then the next thing that we need to see is the preparation of alkynes. How do we prepare alkynes? Well, in some way, the good news is that there is a similar way as the preparation of the alkenes. Alkenes, we were making those by dehydrohalogenation of alkyl halides. In this case now, for the preparation of alkynes, we can do that from dihalides. So if we have a dihalide, then we can perform a tandem elimination. We can eliminate twice the bromides. So let me give you an example here. So if we have this with a couple of halogens here, so I can perform a dual dehydrohalogenation using a base of appropriate strength. I can use something like KOH. I will need two equivalents because I want to eliminate twice the bromide and the hydrogen. And then the product that I will obtain, if this is my carbon 1, 2, 3, 4, 5, 6. So I will end up with a triple bond between carbon 3 and 4. And I will have still my carbon 2 with that sort of isopropyl there. And then my carbon 5 and 6 are still attached there. So that will be the product of this. Okay, so there we have the method of synthesis of alkynes by going through a double elimination. Elimination once from this bromine and this hydrogen, a second elimination between this bromine and that hydrogen, that will make me, will allow me to form a triple bond. Then we have the addition of bromine or chlorine to a triple bond. If you have enough halogen, if you have enough bromine, you can go through one addition of bromine and then you can go through a second addition of bromine, and the product that you will obtain will be a dihalo compound. So we end up with the tetrabrominated compound. And then we have the addition of HBr or HCl. The interesting thing here is that the reaction proceeds with Markovnikov regiochemistry. That means that the carbon atom that initially had more hydrogens, that is the one that will go with the hydrogen, and the carbon atom that initially had less hydrogens, that is the one that will end up with the halogen. And then we have the hydration reactions of alkynes. Hydration reactions of alkynes, again, they come in two flavors. You can have the Markovnikov process that is mediated by mercury salts. In this case, instead of using mercuric acetate, we are using mercuric sulfate. And then the other method is a non-Markovnikov process that involves reaction with borane in the first step, and then in the second step you have reaction with hydrogen peroxide under basic conditions. So I will stop here this video because I cannot make my videos too long, otherwise I cannot upload them on YouTube. So I will stop here.